Hello and welcome to this webinar by SimScale. I'm delighted to be joined today by the Technical Director for Monodraft Limited, Mr. Nick Hopper, and today we'll be talking about engineering products for a net zero world. Let me quickly make some introductions before we start. So SimScale, we are a software company headquartered in Munich in Germany, founded in 2012, and we have built the world's first production-ready SaaS application for engineering simulation. Now, this means that we have a software which is accessed entirely on a web browser, and it's used by architects and engineers and designers all over the world to perform various types of simulation and modeling, including fluid dynamics, FEA, and thermal modeling. Why are we here today? This is an incredibly important topic. We're here today to look at low energy products. So we will take a look at how CFD is used to design and develop net zero energy products for a sustainable built environment. Now, we're very lucky to be joined by Monodraft today, who are well known for the extensive amounts of research and development they do on developing low energy products for the buildings sector, and they're incredibly well known. Most of their products are found in schools, in offices, in healthcare buildings, and all types. And our guest speaker today, Nick Hopper, he will be talking about how simulation specifically and various modeling activities have contributed to that very advanced research and development they do, and how as manufacturers, they're able to quickly iterate and design new products and get them to market. I will hand over now to Nick Hopper. Please do start posting your questions using the questions pane in the GoToWebinar panel, and we'll take them towards the end. And I look forward to hearing a really great presentation from Nick. Thank you.
Good afternoon, everyone. Thank you for that introduction, Agnon.
Nick, welcome so much to this webinar. Really appreciate you joining, and we're looking forward to hearing from you.
Thank you. So, yeah, really pleased to be presenting to you our HVR Zero product. This is a hybrid ventilation system, and it incorporates heat recovery. We started this development. We've been producing hybrid ventilation systems for many years, and this product was launched in January, and we actually started the development during the lockdown process of last year. Just to give a bit of an introduction to Monodraft, we're a UK manufacturer of ventilation systems, and we started in the natural ventilation side of ventilation, so products that use very little or no energy to provide fresh air into buildings. And over time, we've incorporated more and more fan-powered systems up to the point of actually incorporating air conditioning. Within Monodraft, we are a manufacturer, but we also focus very much on the design side. So building simulation is a key part of our process. And that stems from our low energy concepts, whereby it's really important that the design and our products are incorporated correctly, because at the end point, we can't just turn the power up and use more power to solve other problems of the design. So it's a really important aspect that we spend a lot of time on. The other aspect of our manufacture, we have a really high proportion of electronics engineers as well as our mechanical engineers for development. So we have our own firmware, software, and hardware development. All Monodraft products are commissioned by our own commissioning engineers. We also cover installation, but the key part that we do is a servicing, and we incorporate monitoring. So for the last 10 years, all of Monodraft products have data monitored room performance for temperature and air quality, and that level of data feeds back into our building simulation and development of our products. So HVR Zero started off as a ventilation conundrum that I posed to our company 2 years ago, whereby we want to provide ventilation to buildings, but we need to provide year-round comfort using the least amount of power, but also the heating energy as possible. And that's very easy from a manufacturer to get sort of taken down a line where we really study the amount of energy our products use, but without considering the actual overall impact of the whole building. It led on from things like, our hybrid products we developed 7 years ago. We've installed approximately 10,000 units now, but leading on to that net zero, zero carbon passive house discussion and the greater requirement for low energy, zero carbon systems. It incorporated legislation changes for education in the UK. BB 101 is a key document, and that was leaning towards net zero aspects and utilising future weather files. And also the acoustics are a key criteria for designing ventilation systems. It currently defines the performance limit for our hybrid range. So this is some site data. This is where we started off with the design process. We looked at our previous room data, and this was a school that I knew relatively well. And it's on the outskirts of London, so not urban location, but it's relatively well known to us. And this was data taken from, on the graph on the right-hand side, is the average temperature data taken across July 2018. And this building was designed in around 2014, and so it used the DSY weather file, the design summer year. But what you can see there is I've overlaid the average weather file. So the dark blue is the DSY, the 2020 is in the red, and the 2050 is in that light green colour. And the orange line is the actual temperatures being recorded by our systems. So there's a couple of things that's noting. One is that there's localised warming. So from the solar gain onto the brickwork, it's pulling off heat from that. But also that where the temperatures being experienced are warmer than expected from the weather files. And at the end of this year, last year, we concluded that 2020 was the warmest decade. So the site data is backing out what we're actually experiencing in real life. If we look at wintertime design, though, we carry out a sort of steady state type calculation to determine the sort of ventilation heat losses that are experienced in buildings. And generally speaking, we design to a -3 weather condition, and we'd be looking for 6 litres a second per person. And that provides quite a high ventilation heat loss when heat exchangers are not utilised. We offset the occupancy gains for those because our systems are driven by demand control strategy, so they're air quality CO2 driven, so we offset those gains. However, you still end up with quite a high wintertime design load. So taking that forward to zero. So for zero to us, it meant 3 things. One was to look at this energy balance point to see if we could get to a zero perspective. And the other ones are the zero embodied carbon and the operational carbon. And I'll come on to those points later. But if we carry on with that heat loss calculation, well, if we were to include the sensible heat gains in the spaces and look to incorporate a heat exchanger, what level of efficiency do we need to get to? Bear in mind the levels of temperatures we're recording from our systems and the use of future weather files being used. What we were starting to look at now is actually a -1 wintertime design condition having a heat exchange efficiency of 41% and actually ending up at a wintertime design condition of a balance point of 0. So what that enables us to do is then look at the optimum efficiency of a heat exchange design within the room space and recognize that yes, -1 will be, below temperatures below -1 will be encompassed, but it's limiting that a level of heat loss to a sort of an average condition. And then looking at the lowest possible fan power that we can incorporate within the ventilation device so that we can use the system year round to provide comfortable conditions during summer and recognize that energy penalty for temperatures when it does go to say -5. If I look at the zero carbon now, so we've got the embodied carbon and the operational carbon, When we designed this product, we were looking from the starting point to say we needed it to be zero carbon. And that led us to quite a lot of material choice conclusions. So we really wanted to be able to narrow the embodied carbon from effectively digging it out of the ground, processing the material, through to production of components, through to shipping to ourselves, the assembly process, and actually distributing it out to clients. And that led us to narrowing the number of materials we used in our product, and I'll go on to that section later. But in the end process, we've utilised life cycle inventory databases to be able to assess the actual carbon, the embodied carbon of our system, to 265 kilograms. We've rounded that up to 300 kilograms of CO2, and then we are using a gold standard UN accredited carbon offset program to offset that embodied carbon. On the operational carbon, and this I feel is more on the marketing perspective, that it's a very tangible aspect, is we've committed to plant a single tree for every product that we sell of the HVR Zero. This then provides the end user with a certificate, but also we incorporate that into the building program as well, so that the contractors actually get a certificate of that operational carbon. And again, it's a tree planting scheme that's fully accredited. However, due to the low specific fan powers that we've been able to enable through this system, I actually think we'll end up towards a carbon positive system. And I'm looking forward to reviewing the data we have over the next several years to actually see if we can get to that point. So the CFD design-led process, and this was absolutely intrinsical in the design of this product. I'm really pleased to be working with some very good engineers, and I have one of them with me, one of my colleagues with me, who's going to present some of the CFD work later on in the presentation. But the CFD-led process was absolutely intrinsical to us maximising the ventilation flow rates through our system, using the least amount of fan power possible. And by doing that, we have a knock-on effect that not only do we use less power for the flow rate delivered, but we make less noise through our system. So the acoustic improvement is also there. However, we took that stage further with the CFD and actually maximised the design of the unit to thicken components in key areas. So again, minimise the amount of acoustic noise transmission. Within the design itself, it incorporated chamfered profiles within the air outlet stream. So these areas here were fluted designs so that we maximised the amount of performance through the system, but also absorbed the acoustic range across the system. So this is what the end product actually looks like. If I talk through the sectional design, the system has an extract fan included at the rear of the unit, and this has the ability to draw air through the heat exchanger. The heat exchanger itself is an aluminium heat exchanger, but it's a very low resistance, and the fin spacing is much wider than conventional heat exchangers. This reduces the pressure through the system, reducing down the fan power needed to drive the ventilation air, but also it provides a solution where we don't need to do high levels of filtration. And as such, again, that has a knock-on effect of reducing down the specific fan powers. The unit itself is constructed from expanded polypropylene, and that material is a steam-fused material, and it's a fully recyclable material as well. And being fully recyclable, that was an aspect that we wanted incorporating within our material selection all the way through as well. EPP also provides an internal and an external moulding process. So when we're looking at design of a system, being able to mould the internal shapes as very complex profiles really fed back into the CFD process. The acoustic profiling of the system, I spoke about the fluting arrangements at the front edge of the unit, but we've also got 3 cavities within the front section, and they're actually Helmholtz cavities. And what they do is we are able to tune the frequency of the noise coming from our system, and we actually take it from away from the spoken range. So for educational environments, where this system is mounted in classrooms, for instance, we're absolutely fine-tuning the performance of this system so that it really is operating in its optimum location. Right at the front, we've got a motorised grille, and again, the CFD work was pivotal in this aspect, improving that we were able to improve the thermal conditions of the space by directing the airflow. In winter, we direct it towards the ceiling. We get the Coanda effect and we provide fresh air and mix it through the room. But in summer, the occupants actually improve by having airflow directed towards them. And we were able to prove that we can reduce the predicted mean vote for thermal comfort by having this arrangement. And then finally, to get the optimum quality of fan performance, we're using brushless digital fans, and we're controlling that with our own electronics. Looking for a section of our system, we've got the heat exchanger towards the left-hand side with the intake and extract of air. And on the underside, you can see the two red arrows, with the left-hand side being directed over the heat exchanger and the right-hand side being pulling air from the room into the mixed airstream to further supplement it. And that's that hybrid function of mixing room air with fresh air. You can also see the two thicknesses of material. We've also angled the fan slightly so that it's directing air towards the ceiling. This is all on the acoustic performance that we've tried to really optimize the system. And again, CFD was utilized to optimize that design. This gives you a profiling of all the different airstreams that the unit can select. There are internal baffles and dampers that are automatically programmed. So the unit itself will select the optimum airstream dependent on room temperature, room air quality, and it will maximize the fresh air it can utilize, but also minimize the heat loss. We do two different models. We've got the standard model with a heat exchanger fitted, and we've got one with a water coil, so that we're able to do the primary heating to the space. And back on that net zero, this heating provision, it has been designed from the outset to be used with air source heat pumps. So it's a much larger water coil than would be normally used, and that then meets the lower flow temperatures of air source heat pumps and fits in within the net zero aspect. And just to give you an idea of the engineering performance we managed, if you look at the SFP values on the airflow for normal daytime, we have a SFP of 0.053. That means the system under its normal daytime power consumption is consuming 6 watts of power. And for that, it was nearly 30% of the normal power that our previous system was utilizing on our hybrid ventilation range. There were 3 aspects to the design though. So the first aspect was the actual ventilation system itself. The second aspect was the user controller. And by having all these additional features of different airflow paths and motorized grills that were able to direct air towards the occupants and move them up, there's only so much you can do with panels and buttons. So we actually developed a completely new wall controller. So it's a 4-inch touchscreen. This has 4 temperature sensors mounted within it, and as well as a CO2 air quality sensor. And that enables us to get a very high accuracy level on the temperature reading. And it also provides that ability for us to give user information. So rather than having sort of panels stuck behind wall controllers where people are trying to understand how they interact with a ventilation or building services, we're able to incorporate that within the screen. And the last part of the design was a centralized control. So this then fits within the facility manager's remit, and that allows all our ventilation devices in a building to be linked back to one central point, generally within the plant room. Now, building management systems generally take this part. However, our experience is that the facility managers rarely interact with them and that they're almost afraid of them. So the design of this process was, or the design of this, the graphics for this, we commissioned a graphic designer who I described as pink and fluffy. That was her. She was very good at wedding graphics, and you know, we wanted to go from an outside, from an engineering perspective, so that the end effect is that someone with little experience will be able to interact with the displays and be able to really drill into the units and find out what their performance is. The systems operate from a 4G connection, and we're able to, instead of connecting that data via a data card, we're able to push the data directly out to the cloud and then bring that back to our head office, where we've got AI running automatically to look at fault diagnostics. We're also able to update the software. So we've got firmware updates being pushed out 3 times a year. So the system is always up to date and running on its latest operational settings. And if I just draw your eye to the top right-hand side, that is where the systems link into a building network. And we have developed our own communication protocol based similar to a Modbus type connection, but rather than having a single assigned number, the systems will self-assign. And by having this grid pattern, it means that we can automatically do a self-discovery, and the individual floors will pre-populate with the settings that they find, or the systems that they find. This saves a huge amount of time and saves a huge amount of setup times, where previously things like floor plans are overlaid and rooms are individually assigned. That all adds quite a lot of complexity and time to the installation of management systems. And so by doing that automatically, we've really streamlined that process. So going back to the CFD work, I'm going to introduce my colleague Alex Chandler to you to go through some of the sim-scale modeling that's been done. But from a management perspective, the whole of this development for this product was done during lockdown. And so we went from an office-based R&D team and design team through to people working from Kuala Lumpur or Colombia when they went home. And so, you know, being able to access the power of technology from browser was absolutely pivotal for us. So I'll hand over to Alex now.
Thanks, Nick. Hi guys, so I'm just going to be talking very briefly today about one of the applications that we use SimScale for in developing, and really this particular one was appraising our product and how it performed in a specific environment. So in Britain, it's important from a marketing perspective that our systems comply with certain British standards. In particular, the most strict one is BB 101, which is used predominantly for education. And within this standards, the first outlines criteria is that at occupancy level, which in secondary schools is at 1.4 meters, the bulk average velocity should not exceed 0.2 meters per second. And the second one is that the thermal comfort levels, which can be quantified through a metric known as the predicted mean vote, should be within the range of minus 0.5 to 0.5. So in order to prove this, we set up a simulation in SimScale using certain boundary conditions that you can see on the table on the right, and flow conditions and global settings that you can see in the table above it. In order to get the best possible results and most accurate, we actually modeled the individual occupants within there and wanted to see how each of those occupants were giving off heat and how that interacted with the moving air around it. So our mesh settings for this, we used there were no specialist mesh settings required. SimScale was able to facilitate some really easy pre-made mesh settings. We weren't required to use any separate mesher. It was just the standard algorithm, the snappy hex mesh. So what you see in front of you, the result of this, we used the hex dominant mesh algorithm, which resulted in 21.3 million cells, and the boundary layer that captures the more viscous sort of sublayers closer to the wall. We used 5 boundary layers with a growth rate of 1.5 and an overall relative thickness of 0.4. So the results, looking specifically at objective 1, where we want the average velocity to be below 0.2 meters per second. As you can see from the results, we were able to extract both visual and specific data in terms of being able to read what was going on. So as you can see, at 1.4 meters, 1.4 meter height, we were able to see that the average bulk velocity at that level was at 0.18 meters per second, which confirms that our systems in this specific environment comply with the criteria outlined in BB101. Secondly, in terms of the temperature and the predicted mean vote, i.e. The actual thermal comfort experienced by the occupants within the room, we had exactly the same. Both results showed that we had compliance with BB101. As you can see, the temperature heat map on the left and the predicted mean vote on the right. Yeah, thank you.
So thank you, everyone. Nagman?
Nick, Alex, thanks so much for that presentation. Really, really fantastic. We have some questions coming in, Nick. Should we take some questions from the attendees?
Yes, sure.
I guess a couple of questions from me quickly, just to put things in perspective. Nick, how big is the HVR? If you could give us an idea of scale quickly. That product that you showed, how long is it, roughly?
So actually, we've got the dimensions linked back onto this slide. Yeah, the dimensions of the two models. The standard model is 1250 mil long, 298 mil deep, and 950 mil wide. And I show here the systems that are exposed, without their top casing, but they generally can fit within ceiling voids. So we have a ducted version that comes off and is completely concealed within a ceiling void, or that can be mounted within an exposed arrangement with like exposed surfaces. Yeah.
Okay. Fantastic. We have a question from a member of the audience. He's asking, do you have a pump for the exhaust air? Sorry, do you have a fan specifically for the exhaust air? Or yes. Is it just okay, you do, yeah.
Yeah, no, we have an extract fan. We've got several different. We started off the original design to say, could we just do this through positive pressure? And you know, we were the calculations are there, but not quite. So worst case scenario, we just said, right, well, let's incorporate an extract fan from day one. So yeah, the fan with the black square with the blue circle on the middle, that is the extract fan at the rear of the unit. We're running it quite slowly for that type of fan. However, what that does allow us for, particularly on education where there's a science classroom, it means that we can meet negative pressure for science mode.
Yeah, okay, fantastic. There's a question from Klaus. It's more for SimScale about verification validation studies, I think, what you're asking about. Klaus, if you go to the SimScale website, there's a whole section on documentation and validation. We've published dozens, if not more, validation studies conducted against experimental empirical data, things like wind tunnel tests, other CFD codes. So please have a look at that. There is lots of data we've published, and independent third-party academics have published also data in academic journals. Maybe we can include a link to that in the follow-up to this webinar. So thank you, Klaus, for your question. Nick, a couple more questions. So you mentioned software over the air, SOTA. Could you just elaborate on that? I've not heard that term before.
Okay, so similar to sort of the Tesla car type operation. So where we update our firmware, which the operating system for our ventilation systems 3 times a year, and that's done on general learning of the improvements on how we can operate systems better, reducing down user issues, thermal comfort issues, as well as reducing energy consumption. And so by able to push that out rather than doing a maintenance visit by us visiting site and updating software, it's a real change on procedural and cost effective for the clients. Okay,
great. We have a question from Qasim, who's asking about cooling options. Is there a chilled water coil option available? You mentioned a bit about air source heat pumps. Maybe if you could elaborate on additional heating and cooling.
So yeah, we've incorporated within the heat exchanger, we've incorporated a condensate tray from day one. Going into using the X Plus system, where it's got a water coil that can be used with a heat pump to do a cooling system, requires us to fit a condensate pump within the system. And other than that, we're already developing that product at this moment in time, and we're expecting to launch it to market next month.
Exciting. Okay, Qasim, I hope that answered your question. Please keep posting questions. We have a couple more here, Nick and Alex. So I guess you said you talked about CFD design-led process. Is that standard for all your products, or was it specific to this product?
We have used it before to an extent, but because we had SimScale on this product in particular, it meant that we could do it with more confidence, I guess. And we could look at the idea of a lot of simulation software that I've used before. You can't run them in parallel unless you have very powerful computers.
Exactly.
The nice thing about SimScale was that I was able to sort of run multiple simulations at once and compare them fairly quickly rather than doing them in sort of a linear modular manner.
Yeah,
great point.
I mean, looking at historically, yes, we've used CFD on a development of our products. We didn't use it within regards to the HTM development, and so this was us taking it to the max, really.
Great. I mean, really great points there. You're taking it to the max. I mean, you're pushing the boundaries of design, right? Getting to net zero and net zero products isn't easy. You really have to optimize pretty much everything in the product, not just the product itself, but how it's applied. And you showed some great examples of, the room where you simulated this in the room. And Nick, you've been doing this, for a long time. You've seen a lot of different tools. You mentioned earlier in your presentation that building simulation as well, and various CFD tools that you use. How have CFD tools changed in the last 20 years, in your opinion?
The change is fantastic. Looking at the ability to iterate designs, and the processing capability is fantastic. The graphic outlay from it is fantastic. The opportunities now are so good, and what would have been considered sort of state of the art in that period of time compared to now is so far stretched, and that goes through in all aspects of design. When we started with Monodraft, it was very much there were still CAD draftsmen with people drawing with pens, and now look at where we can 3D print components, iterate lines before we start going to tooling, where we look at the aspects of FEA analysis. We used SimScale on looking at all the components we designed. We ran FEA analysis before we actually fabricated the initial prototypes, and then we're able to lab test with so much more confidence.
Yeah, amazing. And you mentioned some key points there. Alex mentioned about being able to run simulations in parallel to get through those design iterations, I guess, to help you converge on the right design. And you also mentioned about working remotely, that this whole product was basically designed in lockdown, right? I guess it's interesting you talk about people being thousands of miles away from, what was it, Malaysia and Colombia and stuff.
Yeah.
SimScale has some great collaboration features as well, and the kind of support you get. How useful was that for your development? Because I know you have another product coming out next month, and you're known for the innovation that you do, and a part of that is turning around, responding to the market quickly. How useful are those kind of collaboration and cloud tools to help you to do that?
Personally, from my perspective, it was throughout lockdown. I live quite close to the office, so I was able to come in at some points. However, there was a month when it was particularly difficult and I had to work from home. We didn't really have much of a choice. And having SimScale at that point, it was during very much the concept phase of HVR development. So having those cloud tools and being able to work remotely, and also being able to, share screens with, have other people within the office see the project, see the boundary conditions that I'd set up, and the different mesh settings was an incredibly useful thing for us to be able to do, and it made the initial design process a lot quicker and a lot easier for us.
Fantastic. We have another question about filters. Are there any filters in this unit, and is it possible to add bespoke filters in?
Yes, we've got a filter within the X Plus system, just so that the gap between the water coil and the fan is an area where the maintenance is limited. So therefore, we've fitted a mesh filter there, so that for cleaning purposes, that part is accessible. But within the design, we come from a base of natural ventilation with openable windows, and as such, therefore, we've tried to keep the design within that remit of minimum amount of energy use through reduction of the resistance, but also the reduced maintenance aspect. And we know many instances of trying to get our ventilation systems. We sell maintenance contracts in things like schools and colleges, and it's a hard process to get stuff maintained correctly. And by having filters in there, if they're not changed, then the performance is degraded very quickly.
Great. We have a couple of other questions coming in from the audience. Nick, what's next for this particular product? You mentioned the software over the air, so you're getting feedback on how this product performs. You already have the model set up in SimScale. You can run multiple simulations in parallel. Presumably, it's relatively easy to test different components, scenarios, pressure losses to keep improving this product. Is that how you operate?
Yeah, we're going to be looking at the cooling simulation is for in-room use is next. We've got a couple of sites that are going forward with the design, so we're looking at doing some modelling for that, just as more or less as a one-off, as a proving exercise for those live projects. And the product itself is those dimensions at the moment. We're in the pipeline. We've got a smaller unit for smaller offices and group rooms, and then a larger system for larger communal spaces.
Fantastic. We also have another question about CAD tools. So if you could just comment on the different types of CAD tools you use to design your products, and the kind of images we're seeing on screen, and interoperability with for example, SimScale and CFD tools. How easy is that process? Yeah.
Do you want to talk about the?
Yeah, sure. So we predominantly use SolidWorks as the CAD tool, and the kind of process to get from SolidWorks into SimScale is fairly easy. From a lot of the stuff that I do, you draw it, you create an assembly, and then you extract a fluid volume from that assembly, and just import it as a native file type into SimScale. There's been no need to change the file type at all. It's a fairly easy, like, two-step process. Yeah.
And Alex, give us an approximate kind of runtime, like, from the time you hit run to when the simulation converges and you start analyzing. Roughly how long are these simulations?
Well, it obviously depends on the size of the mesh and the nature of the thing, but something simple. I've had some really simple stuff. So when we were actually designing the inside of the unit and we were trying to optimize the acoustic and the aerodynamic architecture on the inside, small sort of elements we were able to do in sort of 3 or 4 hours. However, larger ones, so the ones that we've got in front of you now, with 21.3 million cells, probably slightly longer. I think this one was about 15 to 16 hours. But because, as we've said before, you can run them in parallel, it makes it a bit easier. Once you have a method down and you're happy that it is going to reach a converged solution, you try it with different boundary conditions, and you can set it up and view it in the morning.
Absolutely. And I think the key point you mentioned was the ability to, in a normal sequential process, you run a simulation, you come back, you look at the results, you might make some modifications, you'd run it, you'd come back, it's very linear. With parallel simulations, obviously, you can set off like maybe 5 or 6 different configurations at the same time, and then come back and compare all the results. So that was a great point, Alex. Thank you. We have a question here about this might be more for SimScale, about simulating air quality. So yes, Jog, you can also simulate, obviously from some of the results Monodraft have shown. On top of that, you can have more detailed results on temperature distribution, ventilation efficacy. You can also model using different types of models. For example, passive scalar, you can model and represent pollutants and how they would spread as well. And there's a whole host of other kind of solvers you can use in there. Maybe we can send some more information as a follow-up to that. And another question was from about cloud credits. So this is an interesting one, Nick. I guess it goes to the management of simulation as well. So my answer in this respect is, the question is, do you spend cloud credits if your CFD analysis fails or diverges, for example? Great question. The simulations run on the cloud, so you do consume cloud credits for simulation. At the moment, SimScale doesn't charge for failed runs, with a fair use policy applied to it, because we want simulation to be as easy as possible and accessible to everyone and anyone. That is one of the purposes of SimScale to exist, is to democratize simulation, make it accessible to every engineer. Nick, what's your I guess the cloud is, you have simulation credits or core hours. How easy is it to manage that as part of the design process?
The process of managing it is, I'd have to say, I trust the engineers and to get the optimum solution and not to burn through our year's worth of allocation within 2 months. So far, I haven't had to worry about anything on that. So I leave it to them.
Great answer, Nick. Another question from one of the attendees is about predicted mean vote, the PMV. So I guess from my side, the answer, yes, it's a standard output in SimScale, so it's PPD, and there's many other variables which are standard outputs. Nick, is the PMV and PPD, do you use that to demonstrate compliance then with specific standards?
So PPD and PMV is incorporated in offices and in education, mainly for mechanical systems rather than natural ventilation or hybrid. But the reality is that we think it's a really good way of showing the difference in thermal comfort, particularly as airstreams. We've got the ability to move airstreams between high and low level positions, or swing air between spaces. And so we're also sort of incorporating things as, what is the optimum desk layout? This was a desk layout that was given to us by a client, but perhaps a different desk layout would be a better solution for distribution of air in spaces, which is going to take more prevalence going forward since of COVID.
Fantastic. Thank you, Nick. That was fantastic. Well, listen, Nick, we've had a fantastic time listening to you, and Alex, thank you for sharing the work that Monodraft does, the research and development. Really appreciate your time on this, and it's great to see how you're looking at this from a product perspective, but also a placement perspective. So you're doing simulations at multiple levels, multiple scales, and that's great to see in one team, in one company. Normally you'd see manufacturing companies focusing on components, and then you'd have architects and engineers focusing on the room and the buildings. You guys do it in one place, and I think that's great learning for for everyone else to see how you've implemented that. Nick, some final thoughts on simulation dosoftware tools, SimScale in general. Where does the next 12 months take you?
Where's the next 12 months take? Well, as I spoke earlier, we've got 2 more separate products to develop, which will be taking on exactly the same remit with CFD work to optimize the flow performance. Obviously, we've gained a lot of knowledge in scaling the systems larger and smaller, so we should be able to iterate that quicker. But the modeling side of things is a really important part. We've embedded it within the company for a long time, and it's become a mainstream aspect of our design.
A fantastic thought to end on, Nick. Thank you so much on behalf of SimScale and all the attendees. I want to thank you to Nick Hopper and Alex for joining us and sharing your views and your expertise and knowledge from Monodraft Limited. Thank you, Nick and Alex.
Thank you.
To all the attendees, thank you to your questions. We will send a follow-up email. Thank you for registering, and a recording of this webinar will be made available. If there were any questions we couldn't answer, or you have any additional questions, please do get in touch with SimScale, and we look forward to see you soon. Thank you and goodbye.